Hello again, and thank you for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Thanks for your company. In this show, we answer audience questions, and we've got plenty today. Martin is asking us questions about the Big Rip, or is it the Gnab Gib? We don't know which. Mike is wanting to know what was around before the Big Bang. I think we've had that one before, but we will revisit it. Questions about colliding neutron stars and sunsets on the moon. Ah, how beautiful. Sitting there, looking out over the sea of tranquility, getting covered in dust.
Yeah.
A pina colada that you can't drink because, Never mind. We'll answer all of those questions on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us again to solve all of those riddles is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to hear your conjectured sunset drinks on the Sea of Tranquility. I hope I can join you for it.
Even if you could suck on that straw, lunar regolith probably doesn't taste very nice.
That's right.
Yep. But yes, one day someone will be sitting in a building looking out over the lunar surface, probably, downing a beer or who knows what. Or maybe they'll just have to suck it out of the air in front of them because of the gravity. Who knows? Shall we get down to business and see if we can solve some of this stuff?
Why not?
All right. Our first question comes from Martin. Now, this was a really long, involved question, and I hope Martin will forgive me, but I sent you the whole question, but I'm just going to do the Prayseed version so that we're not here for the next 25 minutes reading out. It's not that long. But anyway, gents, thanks so much for the podcast. That was the question. No, I have some questions about the Big Crunch. Now it seems to be back in vogue. One, is it in fact now the favoured theory? And two, also, if we do get a Gnab Gib, in a lot of ways, it sounds like a super, ultra, hyper-massive black hole with all the matter and energy of the universe gathering to a singularity. Which one is it, and why? That's Martin from Melbourne. Of course, he goes into a lot of detail within his question with, possibilities and ideas and concepts and lefts and rights. But yeah, we have talked about the Big Crunch making a comeback. They're starting to, although we are still seeing an expanding universe, it's just not accelerating like it was, I think. So that's what's brought the Big Crunch concept back into vogue. But at the moment, the Big Rip seems more logical given what's happening.
Yes. So you're
it could be neither.
That's true. You're right that, and Martin's right, that we've seen a lot of discussion about the possible reduction of the acceleration. So the universe is expanding. We've known since 1998 that expansion is accelerating. That is the work that got Adam Rees, Saul Perlmutter, and Brian Schmidt their Nobel Prize in 2011. Now, the recent evidence from the dark energy survey, because we think that's caused by dark energy. We think it's caused by an energy of space itself. That means that as space gets bigger, it has more energy, and so it gets bigger faster. That's the bottom line. Now, dark energy is the big puzzle. What is it? How does it behave? So the Dark Energy Survey, which we've talked about recently, it's presented some results, has suggested that it is that the acceleration may be decreasing, but it's not by any means confirmed. That's still sort of new research. It needs a lot of verification. And even if that was verified, we'd need to know just by how much it is decreasing and what phenomena might lie ahead in order to predict a big crunch or a Gnab Gib, as Brian Schmidt always put it. Not a missing BG brother. Was that Martin?
Yes, that was.
Martin, another Martin who said that, yeah.
Martin Berman Govine.
That's the man, yes. So it's still, I think it's still a fairly speculative idea. I think it's very speculative that we might end up with a big crunch. It's still speculative that the acceleration is decreasing. And I was looking a couple of days ago at another paper, actually written by a big group of authors, including some luminaries from Australia, also Brian Schmidt and Adam Rees, who I was just talking about now. They are also on this paper. They've done a very, very careful reanalysis of the data that basically was what we based the initial idea of dark energy on, the accelerating universe. It's all about supernova explosions. Because there was a recent paper that suggested that the acceleration wasn't real because of phenomena to do with galaxies. But it turns out that, yes, it is definitely real. The acceleration has been firmly confirmed, but what hasn't been confirmed is that it's decreasing. So at the moment, I think the Big Rip is still the likely outcome, that the universe gets so big that space starts tearing itself to pieces. I find that very hard to imagine. I do too. But that seems to be the more likely outcome than a big crunch.
Yeah.
Or it might just keep going forever. Look, we're talking so far into the future now with the observations that we can make at the moment. It's very hard to make any firm predictions.
What I can't get my head around, Fred, is that we've got an expanding universe. It's expanding at an accelerating rate. Makes me wonder how much bigger it's getting every second, because it's expanding out in all directions.
It is. And actually, that's a parameter that we don't know.
No.
Well, no, that's not quite true. There is something that we call the scale factor. It's just a measure of the scale of the universe, and that's getting bigger. So you can talk about the scale factor. You can say that now it's X amount bigger than it was the day before yesterday. But in terms of the physical size of the universe, we don't know. We don't know how big it is. We know that the expansion extends out to the horizon beyond which we can't see any further. But there's more universe beyond that, and it's still expanding. So we don't know how far it goes on beyond that, and that means we don't know how big it's getting. The scale factor is an interesting one, though. It's and it's what you get from redshift. If you measure the redshift of a distant galaxy, that immediately gives you the geometry, gives you the scale factor from that redshift. We call the redshift Z. It's a measure of how far to the red the spectrum of a galaxy is shifted, and the increase in scale factor as you look backward. I should say the decrease as you look backwards. If you look out to a redshift of Z, the difference in scale factor between the universe now and the universe as it was then is 1 over 1 plus Z. It's such a simple equation. Scale factor is 1 over 1 plus Z. That's the change in scale factor, and that's an absolutely rigorous geometrical equation. So we do know the scale factor changes, but we don't know what it means in terms of physical size because we don't know how big the universe is.
No, can't see it. But it must be a massive amount of inflation every second if it's accelerating outwards, and it's already as big as it is. I mean,
yes, that's right.
What's driving all this dark energy? But probably.
Well,
but oh gosh, it's unthinkably huge. But Martin, in answer to your question, there isn't really a favoured theory. They're just theories. So it's at the moment still expanding. Therefore, the rip concept's probably more favourable than the crunch concept. But maybe it won't be either. It might just keep going forever and ever until we bump into something else. I don't know. I don't know. Maybe it'll be the big dint. I don't.
I've got one of those in my car, actually.
Oh, haven't we all? Yes. Thanks for the question, Martin. It's a really interesting one to speculate about. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
Space Nuts.
Our next question is an audio question from Mike.
This is Mike from Chroma in the UK. You had a question, on the podcast I'm listening to, about beginning of the universe, as in the Big Bang. You referred to it as being nothing before it. Surely, from a non-science point of view, it would be better to say there was something before the Big Bang, but you don't know what it was. Why do you refer to it as nothing before the Big Bang? Bit of a strange question, but I thought I'd ask. Cheers.
Thank you, Mike. And I'm going to make a little correction, Mike, because I think it's me who suggested that there was nothing, and I think Fred corrected me and said, well, no, we don't know what there was. Is that the way
something
it went?
like that? Yeah. Something along those lines. It's nice to hear from you, Mike. We have Chroma here in Sydney, which is just down the road from where I live. So you were right to put the words UK after, or the letters UK after Chroma, the original Chroma.
We've had a few of these recently with people from Vancouver in the United States.
Yes, right.
Where was the other one? Which wasn't where we normally think it. Yeah, anyway.
Well, yeah, it depends on your perspective, doesn't it?
Yes, of course it does.
If you're in Britain, Chroma's in the UK.
Yeah.
I mean, you can say there was nothing. Look, the glib way of saying of the origin of the universe is in the beginning there was nothing and then it exploded, and that might be what Mike's thinking of. But that is pointing you in the wrong direction, because certainly with the best of our knowledge at the moment, and that excludes things like ideas of multiverses, because we simply don't know whether multiverses exist or not. We have a universe that we know had a very explosive event 13.8 billion years ago. We believe it was the beginning because the theory of relativity says that, and relativity, in all the tests we've thrown at it over the 100-odd years that it's been, accepted, it's survived all the tests with incredible robustness. So it's worthwhile believing what it tells you. And what it tells you is that time started with the Big Bang. And so it means that there wasn't, the word before doesn't mean anything because there was no time. It was Stephen Hawking who always drew the analogy that, he said, when you look back in time, it's like going along a line of longitude on the Earth, heading, say, northwards. You keep on going northwards. What are you doing? You're going northwards. You know where you're going. You know what direction you're going in. When you get to the North Pole, it has no more meaning because you're at the beginning. You're kind of at the origin of it. And that's that's the analogy he draws, that the Big Bang, time stops having any meaning. So you can't describe what came before because before doesn't exist.
Okay. I see where he's getting frustrated, though, because...
Yeah, well, we all are.
Yeah.
And that's because we think in a normal 4-dimensional world, 3 dimensions of space and 1 of time.
Yeah.
And time is such a fundamental part of our existence that it's hard to imagine something without time. The most recent work on this looks as though time is actually something that emerges from a much deeper reality. This is what the people who are trying to unite relativity and quantum mechanics say that there's a deeper reality, and maybe time is just an artifact that, in fact, some people say emerges from entanglement, quantum entanglement. Now, how that works, I have no idea, but it's a possibility that we might understand time a bit better with some of the outcomes of some of these theories. And then you might be able to see, well, yes, you're right. Before the Big Bang, there was no time, so there's no before. It doesn't exist.
Yeah. And I just did a speculative question to ChatGPT, what was around before the Big Bang, and it basically said exactly what you've just said.
That's good. I'm glad to hear that.
One of the answers is nothing. Another one is that something from nothing, a quantum origin, a previous universe, which is the bounce model, eternal inflation, multiverse possibilities, or cyclic universes. I don't think we've talked about that before, but and look, the real answer is we just don't know.
No, but imagine if we could really iron out what time is all about, then we might have a bit better idea. We might have some sort of lever on the Big Bang. The only physical, we understand the Big Bang quite well in terms of the chemistry that it generated, what happened in terms of the energy creating atoms. That's all pretty well understood from the particle physics theory. But it's when you go to the first few gazillionths of a second, then all these theories just break down and we've no idea what was going on. But if we could understand time a bit better, then that might lead us some insights. What I was going to say was the only real measurements that we can make are of the cosmic microwave background radiation, and that's been very well measured to try and understand what the conditions were like in the Big Bang. What you're seeing then is something that happened 380,000 years after the Big Bang. So you're not talking about the first gazillionths of a second. Yeah. You're looking at a bright surface, which corresponds with the time when the universe was glowing brightly.
Yeah. My theory is that God was making breakfast, cracked an egg, and that some of the whites slid out of the side of the fry pan and hit the hot plate, and there was a Big Bang. That's what I reckon happened.
Yeah.
Which also proves the theory that the egg came first. So I solved two problems.
It's two problems at once.
One go.
Nobody can say you don't get good value for money from space nuts.
Very true.
Especially considering it's free.
Yeah. Unless you want to, but that's optional.
Unless you want to, that's right.
But all voluntary. Mike, can't answer the question really. We don't really know what was around before the Big Bang, if there was anything, I think would be the bottom line. Thanks for the question. Thanks for sending it in. This is Space Nuts, a Q&A edition with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Rightio, our next question is from Colin. When two neutron stars collide, do any fragments break off? If so, there could be billions of such ultra-high density fragments loose in the universe. What would an impact mean for a planet like Earth? Thank you, Colin. You make us feel very cozy and safe now. After that one, I would imagine, because neutron stars are renowned for their intense gravity, are they not? Would it be more or less impossible for a bit to break off and fly off into the universe, or could that happen?
Yeah, you're right, Andrew. They coalesce. They become one object because of the extreme gravity, It's there might be fragments caused, but they'd instantly be sucked back into the neutron star. I think it's probably better to imagine them as two blobs that coalesce together once they collide, with a very considerable release of energy, which we see mostly as gravitational waves, actually.
Yeah, well, we're talking ultra high density in a very small package, aren't we?
Yes, exactly. Something the size of a city with the mass of a star.
Yeah. I think Los Angeles is probably denser. No, I'm sorry. I couldn't help that. That was, I'm not picking on Los Angeles. In fact, I probably picked a bad target because that's a lot of people that would be very angry with me right now. But anyway.
You just lost half our audience.
Yes, I think we did. But no, they've got to understand my sense of humour, but nobody does understand it.
Not even you.
Not even me. But we're talking a really interesting object in space too. Neutron stars are, one of the stories we did it was a while ago now, was about the mountain ranges on neutron stars. Yeah. The highest peaks are like a few millimeters high or something.
Right. Yes, they were.
It's a very, very weird place.
Yeah.
Do we know how they're formed initially?
Yeah, by gravitational collapse at the end of a star's life.
So what class of star would have existed to create a neutron star?
Big ones.
Big sort of super blue giant ones.
Yeah, that's right. That's exactly right. So stars with a mass, I think it's 2 to 5 times the mass of the sun or something like that. It might be a bit bigger. 10 times the mass of the sun gives you a black hole, basically. So somewhere in the below that, but in the upper reaches, will give you a neutron star that will collapse.
Okay, so our star won't do that. It's not big enough to do anything. It's just going to, retire and find itself a street corner with a beer in a brown paper bag and a packet of cigarettes. That'll be the end of the sun. But the bigger they get, the more possibilities.
Yes, exactly. The sun is a non-smoker, but it will do something similar because it will puff off its outer layers.
That happens to all of us. We get fat as we retire, so
yes.
that's what I'm saying.
Yeah. It puffs off its outer layers. It'll become a white dwarf. Will be the nucleus, which itself is an exotic object. That's something the size of Earth, but with the mass of the sun. But its outer envelope will turn into something very beautiful, probably what we call a planetary nebula.
Yeah, we won't think so.
We might not, but this will be a long time after we're gone because we'll have been swallowed up.
Exactly. But as far as a neutron star is concerned, you've got a lot of density in a very small package with a hell of a lot of gravity, and the easiest thing to do there would be to climb the mountains, but I wouldn't recommend it.
No, quite so.
But the bottom line for Colin is bits might break off in the collision, but the gravity is so intense they get sucked back in. So no, we don't have to worry about flying pieces of neutron star hitting Earth while you're trying to sleep. I mean, that wouldn't be fun at all. Thanks, Colin. Thank you for your question. Our final question today comes from Bill in relation. Now, this was an audio question that Bill sent in, but the audio quality was super muffled for some reason, and we couldn't use the audio, Bill. But sometimes these things get messed up in the ether. So I listened to it about 4 or 5 times, and I hope your name is actually Bill, and I hope I got the words right in the question. But he's basically saying, in relation to the Artemis astronauts witnessing the solar eclipse and seeing the sun's corona, would you see the same effect standing on the moon during a lunar sunset? And Bill's in Dover, and Judy and I were in Dover last year. It's absolutely wonderful there. Went to Dover Castle, went down into the World War II tunnels, although they've been around a lot longer than that. Fascinating place, and the white cliffs, and looked out over the English Channel, and it was a clear day, so I could see France. Something I've always wanted to witness. The locals are probably saying, "Oh gosh, he's boring." I can see that every day.
They might like to see a kangaroo, though, which you could see every day.
Yeah. Well, it's a pest species.
Yes,
because they've really adapted to life post modern agriculture, and they're doing well. Yes, now we'll go back to the Artemis astronauts because they did see, when they went around the moon, they saw a lunar eclipse and witnessed the corona. They saw a few other interesting things as well, like impact flashes on the lunar surface from micrometeorites. Could you see the same effect standing on the moon?
Yes, the answer is yes, because the moon doesn't have an atmosphere. What there is on the moon is something called levitating regolith, which is soil being lifted. The lunar soil part is basically the lunar dust, very, very fine dust. And that gets electrostatically charged up during the lunar day and tends to fly off the surface.
And that's why it ends up in your pina colada.
It could be. Yes, that's right. So that's right. So there's there could be a little bit of a dust haze on the moon, which might spoil your view of the corona. That's the only thing that I could think of that would. That it's certainly true that the Apollo astronauts, several of them, yes, looking for exactly what we're talking about, the corona of the sun as it rises above the limb of the moon, they could see this lunar dust being illuminated, and that's how we know it happens. There are some quite well-known sketches made by some of the astronauts because it's very, very faint, and with the cameras they had at that time, it wasn't possible to directly record it. But there were sketches that they made. So it wasn't a solar phenomenon, it's this levitating dust. But I think you'd see the lunar corona as well from the surface.
Okay.
Maybe one day somebody will find out, because at the moment we've never had a human watching a lunar sunset or a lunar sunset or sunrise.
Yes. Yeah, it'll happen. It'll happen.
It will. Yes, it will.
The way they're talking, within a very short period of time, there will be permanent habitation on the moon of some kind. Research stations, maybe. Power generators. I don't know. They've got. There's a lot to do, and as we mentioned in the last episode, they're already looking at ways of building infrastructure on the moon using moon dust. So, we'll get there. I was going to say eventually, but I don't think it'll be eventual. I think we're at the dawn of it.
Yep.
So
very exciting.
But yes, a sunset on the moon could be quite fascinating. And thank you, Bill, for your question. Hope all is well in Dover. And if you've got questions for us, please send them in to us via our website, spacenutspodcast.com or spacenuts.io. Click on the AMA button at the top, and that means Ask Me Anything. And you can send in text questions or audio questions if you've got a device with a microphone. You're all set. And that's just about everything these days. And don't forget to tell us who you are and where you're from, and have a look around on our website while you're there. And please leave reviews wherever you listen to us, because they help. Apparently, I don't know what they help with. Probably someone else getting paid. I don't know. But yes, reviews are always good. They move us up the pecking order. Number 1 in Iceland. Woo! But yeah, it's all good stuff. And Fred, thank you so much. It's been good to talk.
It has. It's been a great pleasure, as always.
We'll catch you soon. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because he likes pina coladas and walks in the rain. Not much into health food, but he's into champagne. That's why he's under the table. Couldn't join us today. And from me, Andrew Dunkley, thanks for your company. Some people will get that joke. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at bytes.com. This has been another quality podcast production from bytes.com.